Hey, hi everybody. I am Prosenjit Saha, and today I'm going to give you a reference of some of the architectural reference from GCP, from AWS, and then I'll take you through the architecture reference of Elasticsearch, and then I'm going to take you through the architecture reference of Looker. So Looker is a BI tool, and I'll give you some information on the Looker, what exactly it does and how can it help, and the architecture reference of the dev test of the Looker application. And then apart from that, I'm going to also take you through some of the reference architecture for the power for AWS and GCP, MLOps and all. So, let me quickly share my screen, and we'll start once the screen is available. Yeah, so I believe the screen has been shared, and let me. Okay. All right, so I'm going to give you architectural reference of initially I start with the reference architecture for MLOps, that is in GCP. So what is MLOps? MLOps is nothing, it's a kind of machine learning operations where the DevOps team and the operations team and the ML, that's the machine learning engineers, operate and interact so that the pipeline can be automated. And over here, I have shown the reference architecture for CT, the continuous testing. However, you can also deploy the continuous delivery, continuous testing, continuous integration, and also you can create the completely DevOps lifecycle for the MLOps. But to make it very crisp and very, very, very small, I have kind of created only for the CT, that is continuous integration. So what I'm going to do is that I'm going to explain you how the continuous integration works and how you can kind of deploy your machine learning in the GCP. So before I take you through the MLOps pipeline, I just wanted to make you understand that how the MLOps pipeline works. So before you start with the MLOps steps, you have to understand how you can the MLOps project, how the project is being segregated, about how the project includes the MLOps engineers or the researchers or analytics people and the data science people. It might also include some of the kind of natural language NLP. Like suppose you're using a time series forecasting like FB forecast, or you're trying to use the some of the high-end RNN or CNN, or then you are trying to do the text mining. So you might use the NLP and NLP processes, and at the same time you might also have some kind of structured data like the time series forecasting, and all those things are there. So initially what you can do is that you can create a data analytics pipeline, you can do a feature store, and you can trigger it and do a data validation, data preparation. This is all your lifecycle data lifecycle. Data lifecycle comprises of your complete EDA, your feature engineering, and then model evaluation and model validation. So once those things are done, you kind of pipeline your source code, and then you can define the pipeline with the source repository, and then pipeline is deployed kind of thing. And this has a kind of deployment. Now the ML is a kind of experimental in nature. What you can do is that you can create a different features, different algorithms. Suppose you're doing the KNN. So in the KNN, you can define the value of the and it can define the value of the trees, how the trees are integrated, how the different trees have been connected. Suppose you're using decision tree or random forest, or say, for example, you're using the ARIMA models in the time series forecasting. How do you kind of define your whether the data is stationary or not? So I'll not go deep dive into the kind of ML, what MLOps, what are the different kind of algorithm we're gonna use, and how can you tune those algorithms and all. I'll not jump into that. I'll create a separate video for that separately. But however, as of now, I'll just explain you the testing strategy. So testing an ML system is a kind of more involved than testing the software test system. So in a software test systems, things are different. But however, when it comes to the ML testing, it has to be very, very quickly. It has to be kind of tracked probably, and then if you're kind of doing the data drift, data drift has to be very, very crisp. You have to understand what kind of algorithm you're using. Suppose you're using a Kolmogorov test and all those things, KS test and all those things. You have to kind of understand your anomalies, and then you can create the automated pipeline to the data extraction, validations, and all those things, data preparation, all those things. That's a kind of a batch fetching can do with the data and all those things. Now, the deployment system in the kind of in ML deployment isn't kind of it can be an offline train ML model as the prediction services works on, and the ML system can require you to kind of deploy a multi-step pipeline to automatically, retain and deploy the models. This can be automatically done, and the pipeline can add complexity. It requires you to kind of automate the steps, and you can either do it manually. But first of all, if you do it manually, then before deploying by the data scientist, the train and validation of the new model has to be done manually. Post that, you can automate your entire deployment in the ML model. Now, in the production, what happens, in the productions, your ML models can have reduced performances. Not only, as I said, the data drift might occur, there might be kind of optimal codes out there. You can understand how the Flask API or the Django framework or Fast API is working. So your data extraction, model validation, and the data preparation is one step, and then the model training, model evolution, model validation is another steps, where you define those things through the model registry, and then once the model has been registered, your trained model can be optimized, and then the model serving has been corrected, and then your performance monitoring has been triggered. So this is how the life cycle flows, and then what you can do over here is that you need to kind of track the summary statistics of your data. As I said, the data drift. And the data, they monitor the online performances of your model, and then you can send a notification or rollback when the values are deviate from your expectations. So data drift is an important strategy over here. You can read more about the data drift, how the data drifts work, and all, and in your further study. So you can work on the data drift, how the data drift detection is done in the Python, what are the different libraries that are available for that, and how the importance of the data drift is in the life cycle of the data science. So those things you can do it later. You can kind of understand your recovering phase, your gradient drift, and your subtitles drift, and covariant drift. So you can understand all the drift processes and all those things, how the data retrieval modeling and the testing of the statistics is calculated. So those things you can do it later at your ML stage. But however, this is mostly into the kind of deployment stage where you kind of define your CI. CI is no longer only about the testing and validation code and the component, but it's also about the testing and validating the data and the data schemas and the models associated with it. And apart from that, you have the CD. The CD is nothing but your continuous deployment. And now continuous deployment is no longer about a single software package. You're not doing a single software package deployment or a service, but the entire system, the ML training pipeline, that should be automatically deployed to the another service, like the model prediction service over here, which is mentioned in the pink color. This one, you have to use this services, GCP. And then you have the CT. CT is nothing but your continuous testing, where a new property or unique to the ML systems, that concern with the automatically retraining and the serving the model. That happens automatically. So those are the steps you need to follow. And the ML steps, I'm not going to do the data extraction steps and all those things. These are the kind of the propensity of the data scientist to explain. But however, I'll just take you through some of the terms over here. The data extractions, like it's a kind of a select and a kind of integrate the kind of data, how we kind of extract the variables, required variables of the data. So it's a kind of this can be automated. You can automate your completely EDA platform. You can do it with a single one-liner code. You can understand how your data, like what kind of data you have, how you kind of use the different statistical tests, like the hypothesis testing, null hypothesis testing, parametrical testings. You can do all those testings and all those things, variable testings and all those things you can do. And yeah, those statistical tests can be done. You can also do you can understand how the data is skewed or not, if it is rightly skewed, leftly skewed, what test you can follow for your skewness of the data. So I'm not deep dive into the data science theories over here, but I'll just take you through the model evolution part. So yeah, so let me explain you the model script, how this works on there might be a few challenges over here with this architecture, and the major challenges, which is that kind of this, you have to actively monitor the quality of your model in the production. That's very important. Unless you monitor it, it's not going to help you. So the monitoring is very important. You have to kind of detect the performance degradations over the period of time. You have to understand how the model has been getting the staleness of the model, how accuracy of model is. Machine learning is very important to track your model over the period of time. Maybe you kind of create a new set of data, and you can see with the new set of data how that model is performing. That's the reason your data drift is very important. So you can integrate those things. And the frequently retrain your production model, how frequently you can retrain your production model to capture the evolving and emerging patterns. That's very essential to capture the essential patterns in the data. And then you need to retain your model with the kind of most recent data. That's what I was trying to explain, the data drift process, and then how we continuously experiment with the new implementation to produce the model. To harness the kind of latest ideas and kind of advance in technology. What you can try to implementation is that you can do a feature engineering, you can do a kind of model architecture, and then you can do some hyperparameter tuner, which I said in the beginning of the presentation. This suppose whatever algorithms you're using, you can do some kind of testing strategies in a high statistical test. You can do some kind of data drifting strategies. You can understand how the data drift process works. So yeah, those are the few things you can understand, to work around. And your EDA is also kind of a very kind of important thing over here, like how you are doing the EDA and the feature data preparation. So that's a life cycle of the data science, that has to be properly tested. Also one thing what I want to do is that suppose you are doing a KS test, like the Kolmogorov and Sinmarov goodness of fit test. So you can understand those tests. You can use the KS test, p-value table. You can use the other SPSS softwares and all those things are there. So you can do the test with the data, and then you can understand how it might kind of look and then flow over a particular point of time. Yeah. So the automation can be included. You can include the multiple services. You can do the rapid experiment with this architecture. You can define your CD of the production model, and then you can use the DevOps services for the ML practices, which is the key aspects of the ML practices and the ML model. So those things can be easily implemented, and those are your experimental operations summary. That can be easily distinguish the production model, testing model, and staging model. So you can separately distinguish those things. And I'm not going into the kind of how you kind of decouple the execution agree environment and the custom code runtime and all those things. I'm not jumping into that. But however, as a data scientist, I believe you will have those kind of idea and how your code and automated code and the Python Flask framework and APIs connected and all those things do work. And the investigation of the data is very important, and the data skewness and all those things. Those are the jobs of the data scientists do. So I hope the data scientists, the machine learning engineers, they will do their basic sanity testing and all those things, and before jumping into the final API integration with the consistency and all. Yeah. So another thing which I would like to say is that the feature store. How do you define your feature store? How do you discover availability and reuse your availability feature set? That's also another thing. So you have to understand how you're trying to recreate your code and then deploy the code. At the same time, you have to kind of related metadata, how related metadata is instigated, and how you kind of serve the data features, and at the same time the experimental can go live, and the pipeline component versions that were executed. So that you kind of have to define the metadata management. In the metadata management, what you can do is that you can understand the execution of the pipeline, the start and end date, the time, and how long the pipeline took to complete each step, the pointers and the parameter arguments, the artifact produced in each pipeline, the location of all those validations and all. The triggers, that's very important, how you could do a concept drift of the data, the significant changes in data distributions. Yeah, those are the pretty much basic things you can follow. Yeah, and that's the end of this ML pipeline automation for CD. I believe I've explained those terms. If I'm not, I'll share my email ID so you can write me the questions, and I'll answer those queries to you. Okay, let me jump into the next slide. The next slide is about the kind of the architecture for configuration of redundancy in a cloud. This is about the private connectivity, how you establish the private connectivity in the GCP. It can be through internet, or it's to kind of a local group of connectors. It might be kind of endpoint which has been situated outside of your network. And how do you connect that? What services do you use? What are the challenges are there? And how you make sure that it is completely secure. That's one of the major challenges which we face every other day. So let me explain you all those things. How we can define our triggers, how we can include the multiple cloud services for the configuration and the redundancy in GCPs. The key sources and all those things. So in a GCP, when we kind of define the architecture layout, our architecture needs to be kind of have a multiple features. We need to understand the processes of when we try to deploy the architecture to the VMware software or any other software. So we have to define our zone, how we can deploy the zones, how we can create a virtual network, and then the landing zone has to be defined, and then we have to also understand the kind of how we kind of predict the multiple features and how we kind of create the reference architecture for that. So that's another thing. Now coming into the reference architecture over here in a GCP. So we have to kind of use the multiple services over here. In the multiple services, we need to understand how the multiple services can be defined. What is the connector I'm using for redundancy, and that redundancy connector can be easily integrated in the multiple services. So you have a kind of physical connections has to be defined, and you have to define the VLAN attachment, or you have to define any other reference clusters associated with it. And at the same time, you have to kind of create the architecture for the configuration patterns. So this is about the reference architecture for redundancy. Let me kind of see. Also, you have to see how the availability of the domain is there, how the console is connected, what are the different the routers have been established or not, at least there are a few requirements over here. Like in this architecture, you have a multiple, you have a central US central 1, US central 2. On the on-premise router is also been connected. Now the on-premise router is connected with the IP address. So over here, you need to at least have kind of 4 interconnect connections, 2 connections in one metropolitan area, like one metro, and 2 connections in another metro. And then the interconnect connections has to be kind of the same metro must be placed in different age availability domain. The metro availability zone has to be defined. So you have to define the Google Cloud, and then you have to define your dynamic routing, and then you can define the topology for it. Like you have a zone 1, zone 2, zone 3, and then you can define the kind of places for all these zone. And then you can define the Google peering edge, which is connected to the Google router, and at the same time the interface has been created. Once the interface has been created, then you can establish the reliability, availability of dedicated interconnectivity, and all those things you can create. Yeah, so that's the process over here. All right, so yeah, let me explain you in a simple term, what we have to do is that let me explain you the lift and shift architecture, in a very precise way. So this is I'm trying to establish a private connectivity over here, and in this private connectivity, we are trying to establish the connectivity to an on-premise network using either dedicated interconnect or a partner interconnect. And over here, the topology over here in this particular figure shows that how we can use the interconnect connection in the 2 different metros and different age availability zones. And my target is to achieve a kind of 99.99% availability using a dedicated interconnect. And what I can do is that I can set up the enterprise to Google connectivity zones and the security foundations, and I can define that roadmap, and I can create the simple next level architecture. I can create a kind of dedicated interconnect. Google router can be created, and then I can define my firewall rules, and then I can have a kind of virtual private cloud, and then I can have the compute engine can be interconnected. So this is how it should be, created. And I'll not explaining the entire the features, how I'm trying to use the VPC firewall and target spoke by allowing the traffic only from the NB IP addresses and all those things. I'm not explaining the custom route exchange, how the custom route exchanges work, and how I'm trying to deploy my VMs and all those things. I'll not go in deep dive into that. But however, what I can do is that I can explain you the shared VPC model, how the shared VPC model works over here. Like shared VPC model over here is defined in such a way that the architecture provides a hub and spoke reference network model. So deployment and non-production and can be created, and it can be defined in such a way that by the shared VPC kind of can be connected. I can have an identity, I can have a gateway, and I can have a local compute and a local storage. So my shared VPC connect controls can have limited access to the services that contain the sensitive data, and that's how the VPC network uses it. And the shared VPC is a networking construct that significantly reduces the amount of complexity in the network designs. And with the shared VPC, what I can do is that I can define the networking resources and centralize the, it makes it very easier to manage the centralized accesses, and service project department can configure and kind of manage the non-network resources, and yeah, so that's what I would like to stop this explanation over here, because, I don't want to kind of explain a lot I can explain a lot of things, but however, this is a kind of basic things when it helps to kind of create the private network connectivity and all. And hub and spoke, I spoke about the hub and spoke. Hub and spoke is nothing but it's a kind of implementation of the common and development and non-production and the production patterns. There's 4 environments out there. So hub and spokes helps us to kind of deploy our model and define the highest level of the network availability, and segregation of the environment has been done with that. And it's a kind of concept of the cloud interconnect or the cloud VPN connectivity has been designed in such a way. And we can also do the SD-WAN appliances. We can also do that. We can understand the considerations in this network protocol, and then you can also use the SD-WAN router supported one of the partners. Whatever partners we have over here, you can do those things. You can also create a hybrid architecture if required, and then we can also create the network segregation, network connectivity center, cloud SQL, and data flow. Data flow can be integrated over there. It's a hybrid model, can be integrated. So it all depends on the use cases to use case. We can create that. We can make it bit versatile. We can make it very much versatile for our client to understand it, how they want to use the connectivity from on-prem to the cloud, and how secure parameters are there. We can also define our secure parameters, the firewalls, and zero trust distribution is there. We can use the service meshes, and then they're deployed across the different cloud providers. So you can have a zero trust distribution architecture. That is a separate thing which I would with this architecture. I'll stop here, but we can also jump into that configuration part, how you can have directly allow the MTL routing and gateway policies while presenting the end-to-end MTSL connectivities and all those things. Okay, so that's all here. If you have any questions, I'll share my email ID. You can drop me questions, and I'll be glad to answer them. All right. So next, we will jump into the intelligent product essential reference architecture in the GCP, what it does, exactly it does, what is the advantages of it, and how it can help us to kind of define the kind of roadmap for our products. This, let me grab some water, drink some water. Just give me one minute. All right. Okay. All right. So intelligent product essential reference, what this exactly does is that, this is a kind of reference architecture for, for the senior decision makers of the organization to understand how they connect with the device. It might be a kind of iOS device. It can be IoT device, sorry. It might be an IoT device. It might be a kind of a Watch 7. It might be kind of Apple device. It can be anything, any device which helps us to build a kind of IoT apps on the Google Cloud using this service. This service is called as intelligent product essentials. Now I'll explain you how the architecture works. Over here, the manufacturers, they want to do is that they want to collect the data from the end users, and they want to kind of improve their productivity by adding the intelligence capabilities. That helps the customers, or that helps to monetize their business, or that helps the doctors or medical practitioners to understand the kind of the features of the health or other features of the product. This also helps the end user to understand that their better health conditions, or their better how healthy they are. Not only about the health, it also helps to understand the vehicle detections, the driver safety, a lot of other things are also there. So this documents architecture, tasked with the kind of designing the intelligent product system. And this has been completely on the GCP, and this is highly scalable, reliable, and kind of cost effective, and it's very secure. And we have these are the services we are using. We're using the kind of customer API. We are using the device API on the Cloud Run, and then we are also using the app database and the Firestore. And we are doing the data ingestion with the Cloud Run, and then the Cloud Scheduler is also there. And yeah, so we have to use 4 to 5 services. Mostly we'll be using the following. Firebase will be using for app hosting. We'll be using the BigQuery and the Locker for analytics and the business intelligence. I'll also explain you the Locker architecture at the end, and also Locker architecture at the end. And we are also using the Cloud and the Firestore for the microservices infrastructure. So this architecture comprises of the device telemetry streaming. It comprises of the microservices, the analytics and the business intelligence, the user app, and the anomaly detection. And let me explain you the diagram, the terms. Over here, you have an edge software. So edge is nothing but it's kind of a device, constrained device, or the smart device, which has been used by the end users, or it's a kind of software that has been designed by the Linux Foundation. And telemetry is nothing but it's a kind of read-only data about the environment. Usually they're collected through the sensors. And this data is often referred to as a kind of eyes and ears of the data. And the data that comes from the facial recognition, image recognition, gesture recognition, speech recognition, NLPs, and kind of emotional recognition. So this is a kind of telemetry. And then we have a CRM. CRM is nothing but your customer relationship manager, or customer relationship management. And then we have the ERP, that's your enterprise resource planning. Now, the number of components in this architecture diagram are kind of discussed. Like I'm trying to discuss all those things. Like the components are like the first components over here is the device telemetry streaming. Now, as the device telemetry streaming component, it handles the streaming of the device telemetry data. It helps to kind of create a kind of low latency MQTT and HTTP bridge handles of the data, and then data and pushes data to the pub sub. And PubSub is a kind of a global synchronous messaging services. And then the Cloud Run, what it does is that it kind of then streams and the messages to the BigQuery for storage and archival and kind of analytics. This is a kind of a sub-optimal components of the device telemetry streaming components. And then we have a microservices. Under the microservices, we have a kind of device API microservices. The device API microservices, what it does is that it enables the device interactions, as a kind of device provisioning by the manufacturer, updating the device configuration. It's a kind of a viewing the device status, security, patches, updates, and other security enterprise level solutions it does provide through API services. And the device registry API runs on the Cloud Run and stores the device's data in a kind of Firestore database instances. So it's stored in over there. Now we have a kind of customer API microservices. The customer API microservice is nothing but the customer API microservices. It provides an API for the customer information relevant to the product ownership experience. It helps with a unique customer ID for reference and the customer name. The customer API can will run on the Cloud Run, and the data is stored in a Firestore database instance. And then we have a kind of the user app API microservices. User app API microservices provides an API for used by the user apps. It runs on the Cloud Run and it combines the ownership data, which is again stored in a Firestore, and customer and the device data from the customer and the device API microservices respectively. Yeah, so this is all about. And then how we kind of ingesting the data. We are kind of ingesting the component in a function that loads the microservices data and stored in a Firestore into a data warehouse, BigQuery to be very honest, and it runs periodically in the Cloud Run triggered by the Cloud Scheduler. Yeah, so this is the components we have. And then for anomaly detections, we are using the PubSub that can be used for various subscriber. And the Cloud Run is there. Anomaly detection services runs in the Cloud Run and uses the time series inside API or other backend services to analyze the kind of telemetry data. When an anomaly is detected, the service generates a kind of records in the data warehouse as well as alerts in the PubSub that can be used by various subscribers. I said that the anomaly is done in the PubSub. That is wrong. The alert has been done in the PubSub. PubSub does the kind of notification to various subscriber. So, and then we can also integrate with other systems as well. Like we can define the other systems. We can section recommends from the Google Cloud partners and other parties which are using edge functions such as IoT clients, and all other solutions are also there. We can also include the MLOps intelligence product that can be also done. We can use the third-party IoT providers, and edge IoT clients and OTA updates can be easily integrated with so MLOps with the intelligent product essentials can be done in the same way with the ML architecture I have presented. The same way this architecture can be integrated. Yeah. So that's all with this intelligent product essential reference architecture. We'll move on to the next one. Next one will come into the reference architecture for AWS quantum computing. Now, when I talk about the quantum computing, this is a kind of open source AWS solution, that helps the researchers and the quantum computing engineers kind of to understand and design and run the computational studies in the drug discovery field. Mostly it is used for the drug discovery field. And with this AWS solution, what you can do is that we can access the quantum computers through Amazon Braket. So Amazon Braket is another services we have. I'll explain you what the Amazon Braket is all about. So Amazon Braket, what it does is that it features, it allows us to kind of use the classical computing and quantum computing resources to evaluate their experiment, their values, and such as cost, time, and performance, and all those things. And AWS solutions comes up with an inbuilt sample code for certain drug discovery. They just have to run that code, and they just have to kind of automate those things. And there's some problems like the molecular docking, the protein folding, and all those things are there in the medical field, planning and retrospective in a planning and protein planning, and all protein synthesis and all those things are there. And I'm not well versed with the medical terminologies and all those things, but it helps you to kind of the medical practitioners to understand the quantum computing in that particular field. Yeah. So over here, what I were doing is that the solution, this solution is trying to deploy a kind of a notebook instance to allow the users to conduct the notebook and experiments. The notebook comes with the kind of use cases for the different drug discovery problems, such as the molecular unfolding and RNA folding and protein foldings and all those things. And when we are using it for the first time, it's a kind of the system will mirror and upload the dependent packages required for the experiment. So there are multiple dependent registries and all the same. What you can do is that you can go into the Amazon Elastic Container Registry, where from there we can understand the multiple packages. The Braket is there. Braket hybrid jobs is there for the experiment. We can run those experiments. We can use the Amazon experiment results are stored in Amazon S3, and then We can run the multiple hybrid jobs in one experiment and kind of initiate the events in Amazon Event Bridge when the hybrid job is completed. And the next number 6, which is a kind of event bridge, is like the events which are then sent to the AWS Lambda for analysis and summary. And number 7, the Lambda sends the analysis report to the Amazon single notification service. I'm using a single notification service where the SNS, the all subscribers, whatever subscribers they have, or we have, the subscribe to this topic will receive the reports by the email. This is a kind of optional, and we may not do it, may do it, and then we can also specify the email for the subscription notification when deploying the AWS solutions. Next is number 8. Number 8 is where you kind of define your endpoints. This SageMaker notebook is there to run the code, analyze, and display the results. Yeah, so this is all about the AWS Quantum Computing. It's completely not a new thing, but it's used by the SageMakers, used by the data scientists working on, especially in the pharma or medical researchers and all those people. Yeah. So yeah, these are the services like SageMaker instances already have this molecular unfolding, protein folding, and all the predefined code is all there. They just have to understand the code and run the code as per their usages. Okay, so let's jump into the another reference architecture. This is the web application architecture on AWS. This has been I have already explained. This I got from the Amazon website itself. I haven't created this one. So the reference architecture is well available. So I'll not go much deep into this, as it's already available. So I'll just explain the things which I've been using over here. I have used the route traffic from that client base request path. And yeah, so this is how the route S3 has been defined with the client base, and I have to protect my web application from the common threats. I'm using AWS WAF. I'm using the CDN for the content delivery. I'm using Amazon Simple Storage Services. So very simple thing, simple application architecture. There's nothing much into it. I'm using a NAT gateway. Why I'm using a NAT gateway? It's very simple. I'm using a NAT gateway. It's a kind of network gateway in each public subnet, and how I'm trying to instances are there, how the subnet is accessed over the internet, how this application is exposed over the internet or intranet, how I'm trying to scale the applications, load balancing and basic things, There's nothing much to explain over here. The basic services, you all are aware of all the cloud practitioners are well aware of the services. Okay, so let me jump into the next slide. Next is the Elastic Cloud Enterprise Architecture. So this is very, very important, how the Elastic Cloud architecture has been implemented, and how we are trying to use the proxy, load balancer, the end user, and the admin, how they connected with each other. So Elasticsearch is one of the very popular, this is like Elastic Cloud Enterprise. This has a kind of lifeline URL, like end of life, and is this is no longer supported, but we can still this document still we can use it, for some the key features over here in this architecture is that this is a kind of a service oriented. I had this one very long before, so I'm just showing it. But as we are not using this anymore. This is a pretty old one. Okay, so the architecture, the basic Elastic Cloud architecture, what it does is that it's a service-oriented architecture. It's a containerizing is done using the Docker. The cluster state coordination is done using the Zookeeper and easy access through the Cloud UI. So service-oriented architecture. When I say service-oriented architecture, what I mean is that so service-oriented architecture, and it's a very the Elastic Cloud. What it does is that Elastic Enterprise Cloud, it consists of a number of the core services, and this service-oriented architecture helps us to kind of scale the platform easily. It helps us to access the services via API. It helps to deploy each services independently in their own Docker containerization or containers. So the scale, it helps to scale the platform. Means that different services can have different reliability and performance requirements. So each services can be scaled separately, and the services can be accessed by API. It helps you kind of the improvement to the services without affecting all of the services. And the deployment is very highly secure. Each services is compromised. It's never compromised, and the damage is within a single container, the part of the application state. So that's the kind of the advantages of this architecture. So over here, we are also using the proxies. So we have to understand how the proxies work, how the load balance is connected through the HTTP protocol, and then how the load balance is also connected to the end user of the HTTPS protocol. The proxies, they have a kind of the request mapping clusters and ID that passed in the request, the URL for the container to the actual cluster nodes has been connected through the IDs, and then the association of the cluster IDs is to a container is stored in a zookeeper or cached by proxies. So in the event of a zookeeper downtime, what happens is that the platform can still service the request to the existing clusters by using the cache. So that's a very important features we have. And then the proxies are very if you have a highly available clusters and the nodes are spread across 2 or 3 availability zones, the proxies keep the track of the state and availability of the zones and all. So if one of the zones goes down, then the proxy handling the request will not route to any other request there. So proxies help with the downtime and scaling, and it also helps you to kind of allocators. Allocators are also there. Allocator 1, allocator 3 over here. It's a work on the TLS. Now, they're using a TLS 1.1 or 1.2. I'm not sure about that mostly, but TLS 1.3 has been implemented, which the ELK for the logs and matrices. The allocators help you to scale the Elastic Cloud Enterprise and help on the run. They run on all the machines that we want to kind of host Elasticsearch and Kibana nodes on. So container with Elasticsearch cluster nodes are then run on the kind of machine managed by the allocators. So allocators, they create the containers and starting the Elasticsearch node when requested, restarting a node if it becomes unresponsive, removing a node if it's no longer needed. So allocators does all those things, and it's allocators, they can advertise the resources of the underlying host machine in the zookeeper. So that's one of the kind of the life cycle of the cluster node. Okay, this is how it works. So the cluster with RAM size and all those things that we need to manage. The Docker container can guarantee the share of the resources to the underlying clusters, which kind of mitigate the kind of noisy neighbor effects and all those things. Where one busy clusters can overlooked, or the entire host and all those things can be taken care of. The management services consist of the constructors, and the zookeepers or directors are there. So zookeepers are nothing but zookeeper coordinates the state of Elastic Cloud Enterprise and the state of the all clusters running in our installations. So within the zookeeper is managed by the directors and all. So this is how it works out, and the cloud UI and API, web app API access to the administrative functions and all those things are there. I'll not go deep dive into the containerization using a Docker, tunnel, and all those things, and zookeeper, how the zookeeper is working, the cluster state coordinator using a zookeeper. I'll not go deep dive into that because that's not much that will be completely a separate topic altogether. All right. So let's come into the our last architectural reference. It's called the Looker architecture. So Looker, what does it do is that it's a kind of Looker helps you to kind of it's the BI tool. It's just a BI tool. It helps you to kind of define the your Power BI, your reports. How you can analyze your report. How do you understand the kind of the deployment methodologies, not deployment methodologies, but over here I'll talk about the deployment of one Looker architecture, how you kind of the best practices of the components that are involved and all. So Looker, what it does is that it's a kind of a analytics tool that helps you to kind of create the reports, understand the report, might create the dashboards. That dashboards can be hosted in the Google Cloud. And suppose you are running a machine learning MLOps pipeline, so you can see how your ML pipeline, the end predicted model is can be analyzed through the Looker architecture, Looker application. So yeah. So over here we have to, before we come into the strategy, our strategy has to understand. We have to conduct an assessment to identify what are the list of the planned existing workflow would be, how the applicable architecture patterns would be, how we are trying to prioritize, and then how we're trying to select the optimal architecture pattern, and then the configuration of the architectural components and deploy the Looker application. So we have to understand 4 things before we jump into kind of architectural options. This architecture talks about the dedicated virtual machine, and we can run the Looker as a single instance in a dedicated virtual machine, and the single instance can serve our demanding workload by virtually scaling the host and increasing the default thread pools and all. But the processing overhead of the managing a large kind of Java heap subject to vertical scaling to the those things will come into the picture. But it's generally acceptable for the small to medium workloads. But this is a kind of the complete diagram over here. And I'll not come into the advantages and the best practices and all those things. Those things are not required, but there are a lot of advantages that there is easy to deploy and maintain, and kind of internal database is hosted in a single Looker application. And you can replicate the Looker default SMTP server with your own email notification and schedule task and all. So, so by default, Looker can generate a kind of a bare Git repository for a project. And we can also use a remote Git repository, which can be set up for the redundancy. Looker can start with the kind of in-memory hyper SQL database. and you can define your looker.db or looker the scripts and all those things you can do. You can we generally we recommend to use MS SQL databases for a larger deployments. That is, it can also it's a very lightweight, but it can help you in the performance issues and heavy use and all those things. But all those things are there. Your looker deployment will need to kind of validate to the kind of against the looker licensing services and outbound traffic on a port 443, which is required. And dedicated VM deployment is being scaled vertically by all those things are there. You can define your CPUs and also another thing is that it's a kind of deployment storage is 2 operations are there. Two IOPS per GB is required. Okay, so this is about the Looker dedicated virtual machine architecture. The last one is the dev stage pooling. We can also have the clusters of the VMs, the standard clusters, and all those things are also there. So you can define those things like standard clusters are also there. I'll not jump into that architecture, but I'll just simply explain the dev stage prod. So the use case over here is to prioritize the maximum content uptime to the end users. Separate Looker environment is created at a dev stage and all those things to understand the work requirement and getting the productions. Creating the production environment changes either the deployment time, settings, testing time. It creates a stable environment, work environment. We can define our possibility cases for that. It's a kind of completely interconnected environment over here. It's kind of and this helps you to kind of create a robust robust release cycle. A dev stage product deployment also requires a team of developers who are kind of familiar with the Locker API and a Git for the workflow administrations and all those things. Yeah, so the advantages of this kind of architecture is that if you have a dev test in production, is that the content validation is occurs in non-production environment, that ensures the modifications. The model logic can be thoroughly vetted and it can be thoroughly changed if required before reaching to the production users. And they have a kind of lab features, authentic protocols are there, the data groups are there, caching policies can be integrated, Locker production mode testing is decoupled from production environment. That helps for the single serving and user serving for the multiple users. And Locker can release in a tested non-production environment, give ample time to the new features and implementing all those things. So, you can define your port, you can define the Locker ports and API port. Default port is double line. So all those ports are there. You can define a shared model, and then you can also define a high scaling throughput. You can also create that. So you can define the double line port, Locker server, listeners port only. So those things are there. You can also define your high rendering throughput. Now there are also process can be processed through that. But this is about the local architecture. I'll end my presentation over here. If you have any queries, any questions, please feel free to drop me an email over here. I'll be glad to answer them. That's all for today. Hope you enjoyed the presentation. Thanks a lot.